Swayam Prabha. Digital India. Educated India.
In this lecture, we would like to consider equilibrium equations in 2D polar coordinates. In the last lecture, we have derived the equilibrium equations in the rectangular coordinates. So, in this we would like to consider the derivation for the 2D polar coordinates. These are going to be useful for geometries which are circular. So, under the action of the loading, if you have a disc, it will undergo the deformation, and the loading is going to maintain equilibrium of the whole body, and therefore, at any point there is also going to be, if you consider a small element, that is going to be also in equilibrium. So, therefore, we try to consider a small element here around the point and try to see what does the equilibrium condition mean. So, this element is drawn to a larger scale. We would like to draw it to a larger scale. Let us consider the element to be this one. This is the element. Let us take the reference for theta measurement to be this. So, therefore, let us say that this angle is equal to theta, and center is located there. The other edge of the element is disposed with respect to the earlier edge by an angle delta theta. So, this is the center. Now, we would like to consider that this distance, let the element be A, B, C, D. Let us again assume that the thickness equal to T, which is uniform all over, and this distance AB is very small distance represented by delta r. The stresses that are going to be present in this case are sigma r, sigma theta, and tau r theta, tau theta r, the face here AD face, that is its outer normal is directed in the minus r directions, because r is increasing in this direction, that is positive r direction. So, outer normal is here, it is minus r direction. Therefore, the stress which is going to be normal stress which is going to be positive is like this, that is sigma r, and the shear stress on this face will be represented as tau r theta. So, this will be tau r theta, and since it is a negative phase, the positive shear stress must act in the theta negative direction. Theta increases in this direction, we will consider theta to increase in the anticlockwise direction, therefore, this is the negative theta direction. So, therefore, this tau r theta is positive. Similarly, this AB phase, its outer normal is going to be this one, which is negative theta direction. So, therefore, the stress on this face which will be considered to be positive, it must be directed in the negative theta direction, and it will be indicated as sigma theta. Shear stress which is going to act on this face, it is acting on theta face, and therefore, it will be indicated by tau theta r, and since it is a negative phase, the positive shear stress will be directed like this. So, these are the stresses which are going to be coming on the two faces AB and AD. If we consider that the stresses are continuous functions of r and theta within the body, then we can write the stress on the face BC starting from the stresses acting on the face AD. We can, for example, we can write the normal stress acting here, which is nothing but this is the radial direction r, therefore, the sigma, the stress which is going to be normal to this face is nothing but sigma r. Now, I can write this stress here with respect to this one by the Taylor series expansion, and hence this stress should be equal to sigma r delta sigma r delta r into delta r. So, therefore, this is the stress on the face BC in the normal direction. Similarly, the shear stress which is going to be positive on this face, it must act like this, and its value can be written from tau r theta by the Taylor series expansion as tau r theta delta tau r theta delta r multiplied by delta r. Now, the stresses on this face which is theta positive phase, it will be one component is normal stress, and it must be positive in this direction, that is theta increasing direction, and the shear stress which is tau theta r, it must be acting like this, and therefore, these two components can be written from the sigma theta and tau theta r, and we can write this to be sigma theta plus delta sigma theta delta theta delta theta plus tau theta r plus tau theta r delta theta multiplied by delta theta. So, that is the stress tau theta r plus delta tau theta r delta theta del theta. On top of this, we can also have body forces, and these body forces we would like to represent by the components in the radial direction by x r and the tangential direction by y theta, and let us say that the center of this element is O. AB is delta r. So, let us show it here. Now, we would like to consider the equilibrium equations in the radial direction and tangential directions, and at the same time we would like to consider the equilibrium, moment equilibrium about the point O. Now, let us just do these constructions. If we consider this direction to be local tangential direction and this angle AD making at the center is delta theta, then it is obvious that this angle is going to be delta theta by 2. So, also this angle is going to be delta theta by 2. So, these two angles are same. Now, let us consider the equilibrium equations in the direction r. So, let us consider the equation summation of the forces in the radial direction equal to 0, and this is of course with the understanding that this delta r is tending to 0, delta theta is also tending to 0. Now, if we consider the forces that are going to come up here, we will have the radial direction or rather contribution in the radial directions coming up from sigma r plus delta sigma r delta r and this sigma r, and the area of this face is nothing but r plus delta r multiplied by delta theta into thickness, and this area here is nothing but r delta theta into thickness. So, therefore, these two forces we can write as sigma r delta r into delta r multiplied by r plus delta r into delta theta into t minus sigma r into delta theta into t. Now, you are going to get also this sigma theta acting in this direction is going to also give component in the radial direction. So, therefore, that will be sigma theta acting on this area which is delta r into t, and its sine component sine delta theta by 2 component will be in the radial direction. Similarly, this stress acting on the area delta r into t, its sine component in the direction will its sine component will give us the component in the radial direction. So, therefore, we can write now the two components to be like this: sigma theta acting on the area delta r into t sine delta theta by 2, and it is acting in the negative r direction. Similarly, the other one is sigma theta plus increment of sigma theta multiplied by delta r into t into sine delta theta by 2, that is also acting in the negative r direction. Now, we can consider the contributions of tau theta r. Tau theta are acting on an area of delta r into t, and its component in the radial direction would be cosine delta, this angle is delta theta by 2. So, therefore, cosine component will be cosine delta theta by 2 will be the component in the radial direction, and it is negative r direction, and this component is similar, it is acting on an area delta r into t, and its cosine component will be acting in the radial direction. So, therefore, we can now write these two components to be as follows: tau theta r into delta r into t cos delta theta by 2 plus tau theta r plus the increment of tau theta r acting on the area delta r into t cosine delta theta by 2. So, therefore, these are the contributions from all the boundary stresses. Now, on top of this we are going to also have the body force, and this body force magnitude we can find out from the total volume. The total volume we can take it to be, this distance is r delta theta, this distance is r plus delta r into delta theta. So, therefore, average of that distance BC and AD we can take, we can multiply by delta r into T, that will give us the volume, multiplied by XR, that will give us the force, and therefore, if we write that, it comes up to be XR half r plus r delta r into delta r delta theta delta r into T equal to 0. So, this gives the total contribution, and if we now try to make use of the fact that sin delta theta by 2 is equal to approximately delta theta by 2 for small angle delta theta, similarly cos delta theta by 2 equal to 1, and neglecting terms which are going to have involvement of delta theta square delta r square, we find that there is a great simplification possible. You can see here that we are going to get the contributions like this. Herein some cancellations will be there. So, we will have sigma r into delta r into T plus r delta sigma r delta theta into T minus sigma theta delta r delta theta into T plus delta tau theta delta r delta theta into T plus x r into r delta theta into T, and this can be further simplified by dividing both sides by r delta theta into T. We get from this term delta sigma r delta r, and from this term we get 1 by r delta tau theta delta theta plus sigma r minus sigma theta by r plus x r equal to 0. So, this is the equilibrium equation in the radial direction. It is an analog of the equilibrium equation in the x direction that we have derived for rectangular coordinates. Now, we will consider the equilibrium equations in the tangential direction. So, again we write some of the forces in the theta direction to be 0, and we have the understanding that this delta r is very small tending to 0. So, also delta theta is very small and it is tending to 0. So, therefore, now if you consider the argument similar to what we have done earlier, first of all we are going to get the component in the sigma theta direction to be due to this component and its cosine component, that will give us the component in the tangential direction. So, therefore, it is acting on an area of delta r into T, and its cosine delta theta by 2 component will give us the component in the tangential direction. So, therefore, sigma theta plus delta sigma theta del theta acting on an area delta r into T cosine delta theta by 2, that gives us the component in the tangential direction, and it is in the positive tangential direction, and this one acting on an area of delta r into T again, and its cosine component will give us the component in the negative theta direction. So, therefore, we have now the component here sigma r, I beg your pardon, sigma theta into delta r into T cosine delta theta by 2. Similarly, if we consider the contributions due to this component and this component, they will come out to be, this is acting on an area of delta r into T, and it is at an angle of delta theta by 2 and therefore, if we take the sine component of that, it will give us the component in the positive theta direction. So, therefore, we have written it that tau r theta plus delta tau r theta delta r into delta r I am sorry, I am trying to talk about this component. So, if we try to take this component, it is tau r theta delta tau r theta delta r into delta r, that is acting over an area of r plus delta r into delta theta into t, and this component which is nothing but tau r theta acting on an area r delta theta into t. Similarly, if we try to consider this component, which I have already told you earlier, that this is going to give us tau theta r acting on an area delta r into t, and its sine component will give us the component in the positive theta direction. So, sine delta theta by 2 will be the component in the positive theta direction. Similarly, this one acting on an area delta r into t, its sine component will give us the component in the positive theta direction. So, therefore, since this vector is acting like that, so it will have component in that direction. Similarly, this vector will have component in the positive theta direction. So, they are added, and then finally, we will have the contribution due to the body force, and that body force y theta multiplied by the volume we had calculated earlier, and therefore, this is going to be given by y theta half 2 r plus delta r into delta theta delta r into t equal to 0. Now, dividing the again using the approximations of the type that we have considered earlier, you find that this relationship gets simplified to this form delta sigma theta delta r into delta theta into t plus delta tau r theta delta r delta theta into t plus tau r theta into delta theta into t plus tau theta r delta theta into t plus y theta r delta y theta r delta r into delta theta into t equal to 0. Again, you can make use of the division of both sides by r delta r into delta theta into t, and that gives us delta tau r theta delta r plus 1 by r delta sigma theta plus tau r theta plus tau theta r by 2 plus y theta equal to 0. So, this is the equilibrium equation in the second direction. So, therefore, we have now two equilibrium equation for polar coordinates. Now, we consider the moment equilibrium equation. So, for that we again get back to our configuration. So, we take the moment about the point O equal to 0, and we have the picture that delta r is very small, so also delta theta is very small. You see again the distribution of sigma r plus delta sigma r delta r is such that the resultant acting on this face will pass through this point O. So, also resultant of sigma r will pass through this point. Similarly, resultant of sigma theta and this component will pass through this point, and the forces due to x r and y theta are also going to pass through this point. So, therefore, the moment is really going to be due to this shear component acting on the two radial face and these two shear stresses acting on the tangential face. Now, we are talking of a case wherein the delta r and delta theta is very small. We can have a simple calculation that since delta r and delta theta is almost 0, we can forget about this component. So, therefore, we have stresses like tau r theta acting on the faces whose area can be taken to be the minimum, whose area can be taken by this average spread of the arc here, which is nothing but we can take it to be r, we can take it to be r into delta theta into t. So, therefore, the force, this force is acting on an area of r delta theta into t, that is the area on which it is acting, and then the distance between the two faces is equal to delta r. So, therefore, the moment that is going to come up due to this r theta component is r theta acting on this area r delta theta into t multiplied by delta r, that is acting in the anticlockwise direction. Similarly, if we now consider that the stresses acting on these two faces are tau theta, are only neglecting this this part of the increment, and if I consider the distance between the two to be given by r into delta theta, then we have tau theta r acting on an area of delta r into t, and the distance between the two faces we approximate by r into delta theta, and this moment is acting in the clockwise direction. So, therefore, we have now resultant to be tau r theta into r delta theta into delta r minus tau theta r into delta r into t into r delta theta equal to 0. That is the moment equilibrium equation, and this comes out to be in simplified form that tau r theta is equal to tau theta r. So, what you find finally, that the equilibrium equations of the moment gives us the condition that the shear stresses acting on the two orthogonal faces, they are going to be equal. So, therefore, the shear stress acting on this face and on this face, they are going to be equal. So, to sum up the equilibrium equations here in rectangular polar coordinates, we have the first equation in the radial direction given by this one, and tangential direction, this is the equation, and the moment equilibrium equation gives us tau r theta equal to tau theta r. Now, you can see that since tau r theta equal to tau theta r, it will be also proper to write delta tau r theta delta r plus 1 by r delta sigma theta delta theta plus twice tau r theta and I think I have made some mistake here. So, this should be r, I am sorry, this equation should be r, this should not be 2, it should be r. So, therefore, this is tau r theta by r plus y theta equal to 0. So, that is the form of the second equation. So, we have now, this is the first equation, this is the second equation or its equivalent form, and the moment equation is this one. Now, we would like to consider certain stress state in 2 dimensions, which can be specified uniformly by 3 non-zero component of stresses sigma x, sigma y and tau xy. These states are termed as plane stress and plane strain conditions. If you consider a thin object like this, and if you have loading of the object at its boundary by forces which are at its boundary, therefore, it is loaded in its own plane. It could be loaded like this, or it could be loaded like this, or maybe in combination. So, the loading is in the plane of the body. If you consider this is x direction, this is y direction, and the vertical directions is the z direction, the z face is free of any stresses, therefore, sigma z is 0, tau zx and tau zy is also 0. That state prevails in the face here, top face, so also the bottom face, the same condition is going to prevail. And now we can consider that at any intermediate point, since the thickness is very small, the same state will prevail. Therefore, the stresses which are going to be 0 are nothing but sigma z equal to 0 and sigma zx equal to 0 and zy equal to 0. So, these three components are 0. The non-zero components are going to be sigma x, sigma y and tau xy. So, these are the three non-zero components, and this particular state of stress is known as plane stress. So, this state of stress is known as plane state of stress. Let us find out the relationship between the stress and strain in this case. Let us introduce the material parameters. E as the modulus of elasticity, nu as the Poisson's ratio and G as the modulus of rigidity. And this G modulus of rigidity is related to E and nu by this relationship. G equal to E by 2 into 1 plus nu. Whenever a component is loaded in a direction, there is going to be strain in that direction, and that is going to be coupled with the strain in the other two orthogonal directions, and that effect is obtainable through the Poisson's ratio. So, if we now consider an element of the thin plate which is in a state of plane stress, that element is going to be subjected to stresses like sigma x in the x direction, sigma y in the y direction and tau xy and yx as the shear stresses. If I now consider the effect of these stresses in term, if we just want to calculate the, if we want to calculate the strains out of these stresses, first let us try to see that strain in the x direction. We consider the material to be isotropic, so that there is no shear stress produced by the normal stresses, and therefore, epsilon x is going to be due to only the normal stresses sigma x and sigma y. Due to sigma x, we will have this strain in the x direction sigma x by E, and this is going to be causing a strain in the y direction, which is nothing but minus nu times the strain in the x direction. So, therefore, epsilon y due to this stress is going to be nu times sigma x by E. Similarly, if I consider the sigma y stress, it is going to produce a strain in the y direction sigma y by E. So, therefore, it is going to be sigma y by E, and this is going to also produce a strain in the x direction, which is nothing but minus nu times sigma y by E. So, therefore, this strain is going to be sigma y by E in the x direction. So, therefore, under the action of simultaneous action of this stresses sigma x and sigma y, we are going to have strain in the x direction is epsilon x sigma x by E minus nu times sigma y by E, and epsilon y equal to minus nu times sigma x by E plus sigma y by E. And the shear strain, it is going to be produced only by the shear stress. So, therefore, the shear strain, which will represent by gamma x y, it is nothing but tau x y by g, and this is nothing but 2 into 1 plus nu multiplied by tau x y by E. So, these are the three strain components in the case of plane stress, and if you invert this relationship, if you try to calculate the stresses in terms of strains using these three relationships, you get a relationship which is of this form: sigma x sigma y tau x y is equal to E by 1 minus nu square into this matrix multiplied by epsilon x epsilon y gamma x y. So, this gives you the relationship between stress and strain in the case of plane stress. We will consider the other condition, which is plane strain condition. If you consider a thick plate and it is if we now have the loading of this component by loading like this, we will have sigma x, sigma y. We can also have the shear stresses, and the bottom face will also have the stresses. This side, of course, we have sigma x and this is tau x y. So, these are the stresses on the faces. Now, under the action of these stresses, if we consider our coordinates as usual by x, y and z, under the action of these stresses acting on the four faces, we might have a condition of contraction in the z direction. And if we prevent this contraction by applying forces in the z direction, so putting the load in the z direction, if we prevent this contraction, then in that case what we are going to observe is that all the points which is on a plane parallel to xy will remain in the same plane and it will simply move in the x and y directions. So, therefore, if you consider a plane if you consider a typical plane, this plane which is parallel to xy axis, all the points on this plane will just move in the x and y direction only, and this is a state of stressing which is termed as plane strain condition. Now, in this case you can obviously see that we have epsilon z equal to 0 and we have no shear stress acting on the face. Therefore, we have tau zy and tau zx equal to 0 and we have sigma z is equal to non-zero, and therefore, the stresses again which are also non-zero are sigma x, sigma y and tau xy. So, these are the also other stresses which are non-zero. So, in this case it is a state which is characterized by epsilon z equal to 0 and sigma x, sigma y, tau xy are 0, non-zero. So, again it can be described in terms of the stresses sigma x, sigma y, tau xy. You can also have a case wherein you can allow a certain degree of contraction in the z direction. So, therefore, that will also be a case of plane strain. So, there are two cases possible. You can have epsilon z equal to 0 and epsilon z equal to constant. These are both termed as plane strain conditions. We would like to discuss the case with epsilon z equal to 0. We will show you that the stress sigma z, although it is non-zero, it is going to be dependent on sigma x and sigma y at a point, and therefore, this is a case of two dimensional stress wherein only sigma x, sigma y and tau xy are unknown. This sort of situation is going to come up when you consider a bearing, roller bearing. In the case of roller bearing, think of the roller which is loaded in the radial direction. It is loaded all along its curved surface by radial forces. So, if you have all along the length the radial forces acting, or it is loaded like this, then each plane of this roller will undergo plane strain condition. Similarly, if you think of a hollow pipeline which is subjected to internal pressure, we will find that each cross section of the pipeline will undergo deformation which is more or less conforming to plane strain condition. We would like to find out the relationship between stress and strain in such situations. So, a typical element here is going to be subjected to stresses like sigma x, sigma y, and then we have shear stresses tau xy and tau yx, and also we have the stress acting in the z direction which is sigma z. The normal stresses will produce normal strain and the shear stresses will produce shear strain. That is going to be valid if we assume the material to be isotropic, and therefore, now epsilon x is going to be produced due to sigma x, and it will also receive contributions from sigma y, sigma z due to Poisson's ratio effect. So, we can write now epsilon x to be equal to sigma x by E minus nu sigma y by E minus nu sigma z by E. Epsilon y is going to be sigma y by E minus nu times sigma x by E minus nu times sigma z by E, where nu and E are Poisson's ratio and modulus of elasticity respectively. Similarly, epsilon z is equal to sigma z by E minus nu times sigma x by E minus nu times sigma y by E. And since we have epsilon z equal to 0 for plane strain condition, this gives us sigma z is equal to nu times sigma x plus sigma y. So, in a plane strain state, sigma z stress is related to sigma x and sigma y. Therefore, there are only two normal stresses as unknown in this particular case, and the shear strain gamma xy is going to be given by tau xy by g, and since g is related to E, we can write this thing as 2 into 1 plus nu tau xy by g. So, these are the relationship in the case of plane strain. We can replace sigma z from these two equations, and that will give us, so substituting sigma z, we have epsilon x is equal to sigma x into 1 minus nu square by E minus nu into 1 plus nu sigma y by E. Similarly, epsilon y is equal to sigma y into 1 minus nu square by E minus nu into 1 plus nu by E into sigma x. And we have gamma xy as 2 into 1 plus nu tau xy by E. These are the relations in the case of plane strain, and if we try to find out the stresses in terms of strains, the three components of stresses in terms of strains are going to be as follows. Under plane strain condition, sigma x, sigma y, tau xy is nothing but E by 1 plus nu into 1 minus 2 nu into this matrix multiplied by epsilon x, epsilon y, gamma xy. Now, if you try to write these relations in the expanded form, you are going to get sigma x is equal to E by 1 plus nu 1 minus 2 nu into 1 minus nu epsilon x plus nu times epsilon y. Similarly, sigma y is equal to the same constant will come. So, therefore, we will just write this constant d tau, and this is nu times epsilon x plus 1 minus nu epsilon y, and shear stress tau xy is equal to E by 2 into 1 plus nu multiplied by gamma xy. So, these are the relations for plane strain, and if you look into the relationship that we had in the case of plane stress, we can again write the same expression for plane stress. It is going to be sigma x is equal to E by 1 minus nu square into epsilon x plus nu times epsilon y, and sigma y is equal to E by 1 minus nu square epsilon y plus nu times epsilon x, and shear strain gamma xy, I beg your pardon, shear stress tau xy is equal to E by 2 into 1 plus nu gamma xy. So, therefore, these are the relations for plane stress. So, just to summarize what we have talked here, that in the case of plane stress, we will have only 3 non-zero components of stresses, sigma x, sigma y and tau xy. Similarly, in the case of plane strain too, we are going to have 3 non-zero component of stresses. This is going to be seen in situations where we have thin plate like objects loaded in its own plane, and this is going, plane strain condition is going to be seen in situations where the object is very long and the loading is having some continuity and symmetry in the axial direction. Then in that case, in each plane there will be plane strain movement only, all the points are going to move in the same plane, and therefore, the situation is again characterized by the 3 stresses. And the strains in the case of plane stress are in the z direction, that is going to be non-zero, whereas in the case of plane strain it is going to be 0 in the z direction.